Okay, so next example we're going to analyze the string in series. Okay, we're going to have we're going to find what is the equivalent string stiffness and extension. Okay. So in this example, you're going to have two springs, spring K1 and spring K2. Okay? They are joined at the middle. The first spring is anchored on the left. The right spring is free to extend underneath pull by force P. Okay, I'm going to redraw this, and then you will see how we analyze using the finite element of the matrix method. Bear in mind, you have to keep the practice of how the analysis can be done. So that I will walk with you what is the outline and then later do my hand. Okay. Okay. The reason I need to go through with you is if only you do by hand, then you realize what is the procedure. The left spring is A1. They have not 1 and not 2. They are subjected to force 1 and force 2. In this case, in order to make sure that I express the force to be internal, I'm going to use lowercase. Okay? F1, F sub 1 denote the internal force acting on node 1. And the superscript 1 denote the element number. On element 1, they have left hand side and right hand side. Okay. Then you're going to have element 1. The right hand side is not 2 subjected to force 2. Okay. These are all internal forces. So I'm using the case. Likewise, on element 2, I'm going to have 2 knots, one on the left, one on the right. The left hand side is knot 2. The right hand side is knot 3. Okay, I still put subscript 1 and subscript 2. 1 and 2 representing left and right. And superscript denoting element. Okay? So let's see how do we do the analysis. Okay? So what we're going to do is divide and convert. Okay, previously we had element 1 undergoing displacement U1, U2, subjected to force F1 and F2. I write the equation to be stiffness matrix and displacement vector is equal to force vector. Okay. If the property here is K, if it has the stiffness K, the stiffness matrix is K minus K minus K, K. Okay? So if you try to understand what this means, this is actually an internal spring force. Is equal to your external forces. Okay? If I'm not sure what it is, recall here. Remember how you define the force in knot 1 and knot 2? There are external force 1, and there are, if I move toward the right, I'm going to be subjected to opposing spring force. This is for knot 1. Likewise for knot 2. If I'm going to move toward the right, I'm going to be subjected to opposing force. Okay? This is again the spring force. Okay? Then you have F2. This is how you do the expression for a simple single rod or single truss. But now, this is getting complicated. How this get complicated? If you now have the second spring, okay? This is K2. I have knot 2 the same, knot 3 which is new. This one is going through U2, going through U3. But internally, there must be some force. Okay? I can't be sure that it is equal to external force anymore. Okay? In this case, I still define this as F1, 1 to the left, but other than 2. Then this one is F2. And then, since I'm going to do the combination of the two, I can't express this as F, capital F1, and I'm expressing it as lowercase f1. This is lowercase f2. Okay? What about the equation for the element 2? Okay, I can copy doing the same expression. The force is F1, 2, F2, 2, K minus K minus K. Then this one, I'm going to do re-expression because this is going to be internal force. Left and right. You see this? This, now, I'm going to do the combined analysis. This is element 1, K1. This is element 2. And now the stiffness is K2. So you're going to do the change. Okay? And now, how do you group them together? Please understand the meaning of the free truss equation. The meaning of the free truss equation is what? External force is equal to the internal force. This is for the element 1. For element 2, this is no different. This is still external force is equal to the internal force. Okay? If you now recall your element, you have two truss elements. Your complete model is element 1 and then element 2. They are in series, and now on the left hand side it is straight. On the right hand side it is free to move when subjected to a pulling force. Okay? So what should you do? You should define first the boundary condition. What's the boundary condition? U1, U2, and U3. Among these, U1 is 0. And then next, check out your voltage condition. What's your loading condition? On the left hand side, you have reaction force. So meaning your F1 is negative R. Your F3 is positive P. Do you see here? I have applied, I write the external force as capital letter. Okay? With this in mind, what's the next you're going to do? You are going to write the force sum. So our approach is quite different from the textbook. And most of the finite element textbook. Most of the finite element textbook is teaching you how to do the programming. They taught you like computer. Okay? But for us, this is not our purpose. After you learn finite element, you should better master your mechanics. Okay? So the logical flow of our teaching is we teach you the mechanics first. The procedure will become clear by itself. Okay? Don't do procedure only without understanding the mechanics. Okay? For the complete model, how do you write the equation? Okay? Your equation is we're going to do the force sum. Okay? This is the external force sum. Okay? Is equal to what? Equal to the sum of internal forces. Are you ready? So let's see. How many nodes you have? You now have 3 nodes. Okay? You only have 3 external forces. The first one, if you write F1, F2, F3, they are basically reaction force. On the middle node, no loading. On the right node, a pulling force. So this is the first step you have to bear in mind. Okay? So what's the second step? The second step is look at your internal force. Your internal force is contributed by element 1 and element 2. Since element 2 here, look at here. Where do you have your internal force? Element 2 has nothing to do with the node 1. So there is 0 force acting on node 1. Element 2 consists of node 2 and 3. They're going to have internal force on the left of the element 2 and internal force on the right of the element 2. So this is basically something. Okay? Then next, okay, forget element 1. Forget here. Element 1 is made of node 2 and node 1. Okay? The one on the left is node 1. And then the one on the right is node 2. So we can write this F11, F21, and then 0. Okay? And then do you know what this is? If you are not sure what is it, we can rewrite this equation. How to rewrite this equation into 0s1, 0s2? Okay? You're going to put, this is 2 by 1 vector. How to make them a 3 by 1 vector? You need to add a row of 0. Okay? If you extend them, so we can write them as 0 row, 0 displacement, the stiffness here all together is 0. You might be curious, why do I need to write 0 column at the front? Okay, if you're not sure, you do the expansion. Okay? The first row of the equation, okay? 0 times u1, use u1 plus 0 times u2 plus 0 times u3 is equal to 0 force. You see that? This is the first row of the equation. Okay, I'm introducing u1. This is the force, internal force acting on node 1. Okay, there are no loading. So all these terms are 0. Okay? So this is the force factor, internal force factor. You see that? And then 0 u1 plus k2 u2 minus k2 u3 is equal to f12. Then next 0 u1 plus minus k2 u2 plus k2 u3 equal to f2. Okay? So I'm getting this expression. Okay? And then next, how about the internal force coming from element 1? Look at this expression. I'm supposed to write to do the force vector for the whole all three nodes. Okay? But this one is short of 1. So I have to do the extension U3. In this case, the force coming from spring 1 will not contribute to the spring 3 not 3. Spring 2 not 3. So this one, I'm going to write this is 0 force. And then, in this case, because this is $1, so then my expression here, I have to write them with extension of the stiffness matrix. Okay. So I'm making a new stiffness matrix to account for contribution of the force from element 1. Okay. So do you see that? Now it's time to write the total force. What is the total force? The total force coming from external one is minus R0P. Coming from internal one is F11, F21, and then F12, F22. Remember the row position. Okay? I also have written one this. So now we're going to write force sum. The force sum coming, okay, the first internal force, it is K1 minus K1 0 minus K1 K1 0 0 0 0 times U1, U2, U3. And then plus this one. Okay, sometimes you're going to write the displacement vector first to guide you. Because this is internal force from element 2. The first row and the second, first row and first column are 0. So after you do the sum, what will happen? After you do the sum, this is the matrix simplification. You see that the first row will be K1 minus K1 0. The second, you have your minus K1, K1 plus K2, then minus K2. And then the last row is 0 minus K2, K2. Okay? And then now, how do you solve this equation? These are the force. This is the external load. Okay, is equal to these internal forces. Okay, this 3x3 matrix is difficult to solve, but we apply the boundary condition. What's the boundary condition? U1 0. To do the solution, you do the sectioning of the row where this force is. This row has unknown reaction force. Okay, I don't want to care about this row because this has unknown force. I don't want to solve. Second, you do the sectioning again. I don't want to see the column associated with zero displacement. Anyway, it will contribute to nothing. So in the end, how do you do the solution? You only need to solve for the free nodes. Okay? So you're only solving the displacement on the free nodes. So now we come to the solution step. What's the solution step? So what's the solution step? The solution is solve for free nodes displacement. Okay? Look at this. I have the internal force. Okay? Look at here. I have my external force. Okay? If you now only want to look at the second and third row, your equation is now reduced to this form. What is your equation? Your equation reduced to the force vector is 0 E. It's equal to a part of the stiffness matrix times the displacement on log 2 and log 3. Okay? So you copy it. This is K1 plus K2. In the first row, first column, this is first row, second column. And then next you have the second row, first column, and second column, second row. This is now the, how to read it? This is the stiffness matrix of free nodes. Okay, then this is the free nodes displacement vector. Then this is the external force on the free nodes. Voila, now we can do the solution. How to do the solution? Okay? In this course, I expect you to do solution of 3 variables. Okay? If more than 3 variables is needed, you'll be asked to use the MATLAB supporting. Okay? So for this first course, first lecture, the second example, yeah, you should go back and practice some MATLAB. We also will arrange the MATLAB practice sessions, okay, in the coming essays session. Okay, the solution of this is not limited, so let's see. Let me clear this up and do the solution. So for the solutions, please recall your Fermat's rule. What is a Fermat's rule? If you remember, if you have an unknown xy, multiply matrix A, B, C, D, then the right hand side is something like the force vector, A, B, C, D, E, F. How do you solve for x? solve as the ratio of determinant. In the denominator is A, B, C, D. In the numerator, the determinant is the first column replaced by the right hand side, and the rest stay on. And then how about your y? Your y has the second column replaced by EF, and then the rest remain. Okay, the determinant is the same. Okay. So if you are using this method, how do you do the solution? Isn't that quite a straightforward one? Okay. Okay, let's see what we care about. We care about U3. I don't need to solve everything. I only need to solve U3 because I want to know how much the maximum extension caused by the pulling force P. Okay, now I can write U3 is equal to a ratio. Okay, in the denominator you have the K1 plus K2 minus K2 minus K2 K2. In the numerator, then you're going to have, because you're going to have these columns replaced by the force vector. Okay? And then now you're going to have K1 plus K2 and minus K2. Then in the end you have P K1 plus K2 divided by K1 K2 plus K2 squared minus K2 squared. So in the end, your expression is P times K1 plus K2 divided by K1 times K2. Okay. So what's your answer? Your answer, if I write it correctly, if you recall it, it's going to be force P divided by K2 plus force P divided by K1. This is my solution. So it bring you one important message. What is it? If you are using very standard procedure of finite element, you can solve for the free node solution. Okay? The way you do by mechanics. Okay? The difference is it's all standardized, very standard procedure. Even now you have 3 nodes, if you extend it to 3, 4, 5, 6 nodes, they are all the same way. Okay? And what it's telling you is, you see the extension. If you recall, okay? If you recall the spring, if you recall your mechanics, your Hooke's law, you have now K1, you have now K2. It is subjected to a pull force P. In the static case, left-hand side must be also pull force P. Element 1 is also subjected to a pull force P. The left-hand side of the element 1 is also subjected to the pull force P when it is in static equilibrium. So if you now see, what is the U3 minus U2? It is P over K2. Okay? Right, Hooke's law. Okay? And then what is the U2 minus U1? In this case, U1 is 0. And then the amount of the extension is P over K1. And if you now try to find out what is the total displacement, then you can find, oh, if I do this substitution, okay, U3 minus U2 equals cos P over K2. And this is U2 minus U1 to 0 to the cos P over K1. And if you do the sum, then you have U3 minus U2 plus U2 minus U1 to 0 is equal to P over K1, K2 plus P over K1. In the end, this is U3. After all this procedure, we find that finite element will give you the same solution as your mechanics, the way you practice it. Okay? But in a more systematic way. Okay, so far so good. And this is just the beginning. First and second example. Okay? And a reminder. Every year, when they come to quiz, students can only, some students, I would say, a third of the students can only use traditional mechanics method. Okay, this is not acceptable. Because after learning finite element, if you still cannot use the matrix method, it is a matrix method. Yeah. So you are losing the strength. What is the matrix method? Matrix method is like this. Every element, you write the free truss equation. What is the free truss equation? Free truss equation is internal forces is expressed as stiffness times the displacement factor. The form of the stiffness expressions is the same. It is element 1, you're going to have K1 minus K1 minus K1 K1. You have element 2, K2 minus K2 minus K2, and then K2. This square matrix is located to match with the displacement of interest you want to do for element 1. If we match to element 2 as well, if it is element 2, then the K2 will appear here. This is going to be plus K2 minus K2 minus K2 plus K2. You see that? If you already practice the first, if you now come to practice the second or third, you should automatically know this template can be copy and paste. But copy and paste to different row and different column. Okay? So this is the way of practice. Okay? We're not expecting you every time, oh, write this, okay, and then write the second. But we're not expecting you to every time write many, but you should be able to know the procedure. Okay. It's finite element procedure for the very first transaction. Then next, another pitfall that students have is solution. I also feel not acceptable. Why can't you solve the matrix? Okay? If you already obtain this, if you already obtain this, you must be able to do the solution. Isn't it? Okay? Take the sum. This is in the textbook, they call stiffness assembly. Stiffness assembly is the procedure. The real meaning is the force sum on the free knot. If you already have the force sum on the free knot, and you already take away the constraint node, then you should be able to solve this. Okay? This is simply the practice rule. Okay? You wait until the midterm. You have to start practice this. Okay? By writing. Okay? So your homework is announced. You can start working on the homework. It's due in the 2 weeks later. Okay? Yeah, less than 2 weeks. So please go and practice. Okay? Yeah, this is a happy part. Yeah. And also your okay, you can see the example is very simple. Okay. You can solve by hand. The only new method introduced to you is the matrix analysis. Okay. Okay. Next, we're going to teach you 2D trust element. Then there will be computation. 所以上到这里，大家都在吃老虎。反正这个大一都会解的，唯一教你的就是矩阵方法。但老虎吃饱都不累，我们现在开始要教新东西。So the next question that we're going to cover is, you are all handling 1D trust. Horizontal, vertical. Yes, it's simple, but it's not so practical. In reality, come back to the practical question of inequality. Let's come back to the handbag question. The question is very simple. If you have elastic sling and if you have weight mg, would you be able to find out how much is the extension for the same sling? Okay, how much is the extension? Would you be able to find this? Okay, in textbook I write this is delta unknown. Will you be able to find this? Okay. Yeah, we can use our traditional method. Let's do the force analysis first. Okay, how do you do the force analysis? In this case, you are taking the force